we now come to the notion of satisfaction of a formula in a structure. So essentially, we want to define when a formula says something true about a structure in which we interpret its language. So when does a structure make this formula true? So the first thing we're going to have to look at is the variables occurring in this formula. So far we've looked at the values of closed terms if they do not occur any proper variables in these terms, and that we could simply compute based on the structure, because the structure told us how to interpret the constants and the function symbols, and so I could calculate the truth value of any closed term from that. But the structure does not tell us how to interpret variables. So we need to add an extra piece here, and that's going to be a variable assignment. Right. So the idea is a variable assignment is simply something, a function, that assigns to every variable an element of the domain. So a variable assignment, so we're going to call this particularly a variable assignment for a structure. So a variable assignment, let's call it S, for a structure M is a map S from the set of all variables. Remember, officially they are V1, V2, V3, and so on. We always have that infinite but innumerably many variables in our language. So it's an assignment from the variables to the domain of the structure. So to every variable I say, I'm going to interpret you as that element of the domain. And based on this, we can now go and extend our definition of the value of a term to all terms. Up to now, we've had it for closed terms. Now we can do it for all terms. That was a variable assignment, and now we can look at the value of terms under a variable assignment. Okay, so the notation we're going to use for this is going to be the value in structure M, but now when we had a closed term, we could just say that the value of this term in structure M. But now this doesn't provide us with enough information. We also need to include as a parameter the variable assignment S under which we are working. And so there are three clauses, because remember the recursive definition of terms, apart from the extremal clauses, three clauses. It says variables are terms, constants are terms, and function symbols apply to things which are already terms. So for each of those generative clauses, we need to say what the value is. So if the first option is just for the term to be a constant. So if the term is a constant C, well, then we just ask, what does the structure say? The structure then, its value is what the structure assigns to it. So this is independent of S, exactly the same as we had when we calculated the value of closed terms. All right, the other option is that this term could be a variable, say a variable X, right? Well, then it's simply the value that S assigns to X. And then thirdly, this is the inductive step, if this is a term which is constructed from other terms through the application of some n-ary function symbol. So here I've got f applied to its n arguments, right? So that value is then going to be, well, apply the function to which f is interpreted in the structure, apply that actual concrete function to the values of the terms which are the arguments of f. So you'll see this looks exactly the same as the definition for the value of closed terms, except now we have this additional clause for variables. So, and now we can interpret any term. We can calculate the value of any term in a structure under a variable assignment. So let's look at an example of this. Consider again the language LA of the language of arithmetic and the standard model, so the natural numbers together with the usual interpretation of the symbols as we defined it a little while ago. So with this. Now, suppose I take a variable assignment from the variables into the domain of the structure. So remember, the domain is the set of natural numbers. And I can define this in any way. For every variable, I need to assign a natural number. So particularly, suppose I wanted to say such that S of X is 5, S of Y is 7, and let's say S of Z is 0 for all other variables. All right, so there I've defined a variable assignment. So now I should be able to go and calculate the value of any term. In the previous example, we looked at closed terms. We could only look at closed terms because we didn't have a variable assignment. Now I should be able to calculate the value of absolutely any term. So for example, let's look at this term. If I take, let us take x, and we apply the prime to it twice. We add to that y, and we multiply that with 0 plus, say, x. Right, so if I was to calculate the value of this term in this structure under the variable assignment S, what would I get? So once again, I could go and do this strictly according to step by step, according to the inductive definition of the value of terms, but I'm going to do most of these steps at once. So what is the value of X? Well, the value of X is 5 according to S. So this is going to be 5, to which I apply the prime. So in other words, I'm going to apply prime n, the interpretation of the prime. Now that was just the successor. So I'm going to apply the successor function to this twice. So I'm going to add 1 to it once, and then I'm going to add 1 to it another time. To this we're going to add, now we need to calculate the value of this term in brackets over here. So the y is 7. Here the interpretation of the little fat 0 is just the normal a natural number 0, and x's value is once again 5. So this will give me over here 7 plus 7 times 5. So I get 7 plus 35, which gives me 42. Before we can get to the definition of satisfaction of first order formulas in structures, we need one more notion pertaining to variable assignments, and that's the notion of an X variant of a variable assignment. All right, so where X is now a variable. So we're going to say that two assignments. So suppose I've got two assignments, let's call them S. That's from the set of variables into the domain of my structure, and I've got another one. Let's call it S prime. It's also an assignment, so it sends variables also into the domain of my structure. So these two I'm going to call X variants, and I'm going to use this notation. So this little squiggle or the tilde, X. So I'm going to say S and S prime are X variants. If these two guys agree on everything, all variables, except possibly what they do to X. So in other words, they're variants if S of Y is equal to S prime of Y for all variables Y other than X. So if Y is not X, then these two things need to agree. They may disagree on X, but importantly, they don't have to disagree. They could. Every assignment is an X variant of itself because it agrees with itself on everything, including X. So this is certainly a reflexive notion. You can go and check that this relation, so this is a binary relation between assignments, right? And you can go and check pretty straightforwardly that this is an equivalence relation. If I fix a variable X, then the notion or the binary relation of being an X variant is an equivalence relation on assignments. Go and check that.